the forces as we see them. There's friction in that direction. The only other force, and I guess it's supposed to be 60 degrees, so maybe I should make it a little bit more like that. And that's the friction from the ground. At the same time, it is balanced by a normal force from the wall, also at 60 degrees. Those are the two horizontal forces that act in the system. Now, in the vertical direction, I have three forces. Normal force from the ground, the weight of the ladder, 300 newtons. Now, I don't know where to put the person. So just so that it's in an area of the ladder that is free from distractions, I'm going to draw the force from the person there. The specific idea here is we don't know where that is. We know the ladder is 2 meters long, and we know the weight is concentrated 1 meter from the ground. Or, I'm sorry, 1 meter from the bottom of the ladder. But the person I don't know. So without putting this on the diagram, I'm going to say that that location is a distance L along the ladder. Is that okay for all of you? And they have a weight of 600 newtons. The net force in the y direction is something that we explicitly know. We know it equals 0, sure, but we also know that it's going to be the normal force from the ground minus 300 minus 600. Is there any question about that? That means the net force from the ground is 900 newtons. For all of you who said, I don't know what to do with the coefficient of friction, I challenge you to find in your notes the expression friction has to be less than or equal to mu times the normal force. And dare you to tell me you don't know where the coefficient goes here. Not because I'm angry, but because that was a ridiculous statement. Everybody knows it's mu times the normal force, even in this room where we've studied it for 2 years. Now you might not know what to do next, but to say I don't know what to do with, that might be the wrong answer. But has there, any of this way outside the boundaries? Anything new, anything crazy yet? So all I can write now is the frictional force has to be less than or equal to 0.9 times 600. So I know the range of the frictional force. It has to be 0.9 times 900. Thank you, Cameron, for whispering that question to somebody else, but intending it for me. That means it's less than or equal to 810 newtons. Now, all this tells me is that the frictional force can't be more than 810. But if I'm trying to find where I can stand on the ladder, the maximum frictional force I have to work with is 810. Right? We understand how an inequality works. If not, then your pencil should be writing down feverishly the information you need for the next time this comes up, which could be in the next 5 minutes for all you know. But what I'd really encourage you to do, all of you who are just looking at your crotches and not really doing anything, is to say right now in your notes how to deal with the coefficient of friction when given. Just a thing or two to help you jog your memory that the static friction is a range, and you have to establish where you are in that range. Are you less than that number? Are you at that number? How might you use that? Because I also know in a few minutes, we're going to take a look at the net force in the x direction, which I know has to be equal to 0. And I know in this regard, that frictional force and the normal force from the wall are related. Now, the reason all of this is important was hopefully because of something that was discussed yesterday. That this system pivots about this point. And the people who are standing on the ladder are causing the ladder to pivot clockwise. Clearly, the person, as they move up the ladder, are causing a greater and greater clockwise torque on the ladder. That's worth writing down. If you're having trouble with this and you want kind of a running record of things that you should be thinking about. And this is for everybody who did not get 4.2 meters. That as a person climbs up the ladder, they're increasing the torque on the ladder. Which means they're causing the wall to have to push back more to keep the ladder from falling into the wall. Now, I'm just doing that by looking at these three things. And I know that torque is related to the length of the torque arm. So as this force creeps up higher on the ladder, I need the wall to push back harder. Now, this is the hard part that I think you should transition to. The wall has a maximum amount of force that it can apply backwards before the ladder starts to slide out from under him. We now know what that is. If the friction is a maximum and the normal force has to equal the friction, then the biggest normal force I can have is 810 newtons. I can't have a normal force that's bigger than that. That is my limit, which means the wall can only push back with 810 newtons. If it attempts to have to push back with more, the wall might be able to do it, but the bottom of the ladder will begin to slide. It'll break the friction at the bottom, because that's what's happening. The normal force increases, the friction can't, and so the ladder slides out from under you. So now we have the condition to go forwards. We want to put together a torque equation, which would be the last thing to do anyways. Now, you might not necessarily know that that was what was going to happen, but you did know that you were going to have to, at some point, evaluate the torque. It would have generated another relationship. I just stayed with the force pieces in order to make sure that all the folks who said they didn't know what to do with the coefficient would have some way of understanding that I don't really buy that excuse yet. I want you to use what you already know. Go back to those notes and factor that idea in. So at this moment, I really believe we're at the end of the question. There's not a lot left, but I say that all the time, and I'm not sure that it's true for the vast majority of you. I think you need to see what happens next. So I'm going to do this next part for all the folks who never wrote a torque equation down in their practice last night. That the net torque is going to have to equal 0. And that by choosing a pivot at the bottom, there are 3 torques that act in this system. That the first torque is from the ladder itself, its weight. The second torque is from the person, depending on where they stand. And the last torque is from the wall. 3 torques. I'm going to say that torques that are clockwise or into the board are positive. This means the ladder and the person will be a positive torque and the wall will be a negative torque. The ladder's torque has a torque arm of 1 meter, the middle of the ladder, times the weight of the ladder, times the sine of this angle here, which is 30 degrees, I believe. Now, just looking at that, that's 150 meter newtons. Questions? It's the only one. It's the first one that we can get a numerical answer on. The person, we don't know where they stand, L. We know how big their force is, 600. And we know we're dealing with an angle of 60 degrees. I'm sorry, it's not 60 degrees. Theirs is also 30, isn't it? Sorry. I'm getting ahead of myself. That would have been sad. Now, I can't get a numerical answer here, but 600 times the sine of 30 is just 300 times L. So I'll write that as 300 L. My last torque is a torque from the wall, and I'm going to use the normal force of 810. That's the maximum normal force from the wall. So that'll be located with a torque arm of 2 meters because it's at the end of the ladder, times 810 times the sine of 60 degrees. I can't do it in my head, and I don't really want to try. I know that this will eventually be, let's see, 2 times 8, 1620 sine of 60. And the whole thing needs to be made to be negative. But I don't know what that number is. Yep.
So just to be clear, you didn't use normal force from the graph because that's where the pivot point is?
Yes.
Mm-hmm.
By choosing the pivot to be there, I eliminated both the frictional force and the normal force as possible torques.
So we should pick one that has 2, probably?
If you can. I mean, they're not always going to be like this. It just happens to be this one for this problem. You know, the truth is you could pick anywhere for the pivot. You're just trying to do stuff to make your life easier. Now, if it was actually rotating, you'd have to pick where it's rotating, but it's not doing that. All right, so I'm gonna move on. Are there any questions yet? Because I'm noticing that if I take this, add it up, and set it equal to 0, there's only one unknown, it's L. So my answer is going to be given to me in this expression alone. I don't do any other substitution. So there'll be 150 plus 300L minus 1620 sine 60 equals 0. L equals 4.2 meters. That exceeds the length of the ladder. So they can sit anywhere. Yep.
Can you explain one more time how you know that the torque from the person is positive?
All right. I can explain it a different way than I did the first time, if you would like. First, I could use the right-hand rule for it. I didn't do that before. I just noticed that it was on the other side of the ladder and must cause the ladder to go that way because of where they're standing.
Oh, they're on it. Oh, is that represented by the 600? Okay.
That's the person.
Okay.
Is that enough?
Yeah, I was confused.
Anybody else want me to keep going with that? Yeah?
With like, can you do it like when the ladder was tilted? Oh,
What do you mean?
like how you would find it when it's not flat like that. Like if we didn't tilt the ladder to make it easier,
Okay.
how you would know if it's diagonal.
Well, if you want my opinion, you take your paper and just turn it till the ladder's horizontal. I mean, does that help? If not, then sure. Let me, I would need something clean to work with. I see your hand, Jordan. What were you gonna ask?
But I was gonna say, do you just suggest that we like look at the picture and then you draw it to where it's vertical?
I don't know that I have a suggestion here. Our problems on the exam are probably going to be a little different than this. We're doing some statics now, but there hasn't really been a good statics problem like this in a couple of years. My idea here is that you just need to be able to, you need to be dynamic, meaning you need to be able to roll with whatever is thrown at you. So whatever it takes to find a way to do it, I don't want to make it fixated on this question, but having a system where there's multiple torques, we need to be prepared for whatever we get. So if this is your drawing and you're attempting to figure out the direction of each torque, and that's what your picture looks like, then I can give you 2 or 3 ways to figure out positive and negative. The no thinking way is to draw the x-axis through your torque arm like I showed you the other day, and the y-axis perpendicular to the torque arm. Label that one and that one positive. Put the cross where your pivot point is. Then every torque arm that's in the positive side of x is made positive in your torque equation. So if I was to make my torque equation R, F, sine theta, this will always be positive. But all of the R's that are on the positive side of the pivot point would be made positive. And then any of the forces that are on the positive side of the y would be made positive, and any of the forces that are on the negative side of y are made negative. This is the book's method. It's not my method, but it's the book's method. It will correctly give you positive and negative torques. It might make finding out whether that's clockwise or counterclockwise in your answer more difficult, but you'll get the torques correctly signed so that the ones that are positive will be positive, the ones that are negative will be negative. Okay, Cameron?
Yeah, wait, why was the ladder and the person in the other way? Why were they positive if they're like going down on the negative side?
I'm answering your question by giving you alternate methods.
So it can be different either way you do it.
Since September of 2018, I've indicated that your choice of positive or negative is your choice to make, as long as you are consistent in your application. The right-hand rule, however, is not arbitrary. This is consistent with the right-hand rule indicating a positive direction. So, if the ladder were to rotate based on the right-hand rule, then this way is positive based on our assumption of positivity. In this example, which is the book's example. That's how they do it. Now, how I do it is a little different and will require that you are more subjective. If this is the pivot point and you push this way, what way will it rotate? Are you sure?
Yeah.
Okay. If you push this way, which way will it rotate? Are you sure? You're saying down. That's not a rotational direction, which is why I'm asking, are you sure?
No, clock.
Okay. So if I go back and push here again, what do we got?
Clockwise.
Okay. If I push this way, which way will it go?
Counterclockwise.
All right. You asked like that was a question. But if it's counterclockwise, and this is clockwise, and this is clockwise, you now have a method for deciding which one of these torques you're going to make positive and which one of these torques you're going to make negative. But you have to decide whether clockwise or counterclockwise is positive, or what you're going to do with that. What are you going to do with that?
Positive is clockwise.
All right, so you've said that positive is clockwise. So every one of these ones that you said was clockwise, you would have to list as a positive torque. Any of the ones that you said was counterclockwise, you'd have to list as a negative torque. I have a third option, or is this enough options?
That's enough options.
Okay,
Wait, can you show the right hand?
yeah. If that's where the force is applied, then I need to draw an arrow from the pivot point to where that torque is applied. That's R. Now, I'm not going to do this, you must. And I expect to see every hand in the room doing this, because if I'm spending my time here, you're spending your time here. You must line up your pointer finger of your right hand in the direction of R. If I were doing this, I would turn my paper so that R faces away from me, so that I don't look like I'm doing yoga or I'm a contortionist. Make your life easy. And then leaving your finger pointed along R, merely rotate your wrist until your middle finger lines up appropriately with the force. This might require that you bend your middle finger more or less, but your middle finger can't go on the other side of your pointer finger. So I'm noticing that my hand looks kind of like this while I'm doing that. Does yours? That's how it looks. It's the only way to line it up. And in doing it this way, my thumb points out or away from my paper. By definition, that means the torque from this one is out of the board. Thus, a circle with a dot, because that's the symbol for out of the board. Continuing my right hand rule, that would mean that the ladder is pushed this way and will rotate this way because the torque is out of the board. Thus, this torque causes the ladder to go that way. If you like the word counterclockwise there, then it would be counterclockwise from this vantage point. You still make the final call about whether that's positive or negative. That's still up to you. Again, I have a meter stick, and I have drilled a hole at the end, and I've attached it to the wall in such a way that it can pivot. So a string has been tied to the other end to hold it in place so that it's just sitting there. And what I'd like you to do is, if the meter stick has a mass of 20 grams, is just tell me what the tension in the string is. This is relatively straightforward. But before we go on, I want to make sure everybody can do this. And I am calling out whoever I pick when I pull the little thing out of my cup to tell me the answer. And I want my answer to be in newtons, please.